All right, let's talk about a problem that pops up all the time in tech interviews, the activity selection problem. Now, it might sound a little academic, but it's really all about a simple question. How do you get the most done with limited time? And the best part is, there's a surprisingly simple rule that cracks it, giving you the perfect answer every single time. So to make this real, just picture this. You're in charge of scheduling for a huge conference. You've got one single conference room, but a massive list of people who want to give talks, each with a specific start and end time. Your job is to cram as many talks as possible into that one room without any of them overlapping. So how do you even begin to choose? Here's our game plan for figuring that out. First, we'll unpack the puzzle itself. Then, we'll reveal the secret weapon, the earliest finisher rule. We'll also bust some common myths about how to solve this, prove why our way is guaranteed to be the best, and then dive into the code and its complexity. And we'll wrap it all up with a simple playbook so you can absolutely ace this question if it comes your way.
Okay, first things first, let's make sure we're all crystal clear on what the actual challenge is here.
So here's the official definition. It's called the activity selection problem. You're given a bunch of activities, and each one has a start time and a finish time. The goal is simple. Pick the biggest number of activities you can, with the one rule that none of them can overlap. And that single resource could be anything: a meeting room, a machine on a factory floor, or even just your own calendar for the day.
So how in the world do we find this perfect schedule? Well, the answer is a really elegant idea, a greedy algorithm that I like to call the earliest finisher rule. Let's take a look at a sample set of activities here. I mean, it's a total mess, right? They're all jumbled, starting and ending at different times. Your first instinct might be, what? Pick the one that starts first? Or maybe the one that's the shortest. Where do you even begin?
And this is the absolute key, the big aha moment. Those first instincts are actually traps. The secret isn't starting as early as you can, and it's not about picking the shortest task. The optimal strategy, the one that's guaranteed to work, is all about one thing. Always prioritize the activity that finishes the earliest.
Now watch this. Look what happens when we take that same jumbled list and just sort it by finish time. All of a sudden, a clear path starts to emerge. Activity B finishes first, at time 2. Then C finishes at 4, and so on. This one simple move, just sorting the list, is the foundation for our entire solution.
So the algorithm itself is beautifully simple. First, you sort everything by when it finishes. Then, you just automatically pick the very first activity on that sorted list. In our example, that's activity B, which finishes at time 2. Great, it's on our schedule. Now, all we do is go down the rest of the list and find the very next activity that starts after time 2. Well, activity C starts at 3, so that works. We pick it. Now our room is busy until time 4. So we repeat the process. What's the next activity that starts at or after 4? That would be D, which starts at 5. And we just keep doing this until we run out of activities to check.
Now, before we prove why our finish early rule is the right one, it's just as important to understand why those other intuitive ideas fall apart. This is a super common trip-up in interviews.
Let's look at the two big myths. First, picking the shortest activity. Sounds logical, right? But imagine a tiny 1-hour task right in the middle of the day. If you pick it, you might block yourself from scheduling a 4-hour task in the morning and another 4-hour task in the afternoon. Bad move. Then there's the earliest start time idea. What if an activity starts at 8 a.m. but runs all day until 8 p.m.? If you pick that one first, you've just booked your entire day for one thing, when you might have been able to fit in 5 or 6 other shorter things.
So this brings us to the most critical question of all. How do we actually know that our finish early rule isn't just a lucky guess? We need to prove it's optimal, and we can do that with a really clever technique called an exchange argument.
The entire proof really boils down to this one powerful idea. We're going to show that we can take any theoretically perfect solution that exists, and we can morph it step by step into the solution our greedy algorithm finds, all without ever losing an activity along the way. If we can do that, it proves our solution has to be just as good as the perfect one.
So here's how it works. Let's pretend some genie hands you a perfect, optimal schedule. Okay, now let's look at the very first activity in that perfect schedule. Is it the one that finishes earliest out of all possible activities? If it is, awesome. Our greedy choice matches. But what if it's not? What if it starts with some other activity? Let's call it B1. Well, here's the trick. We can just swap B1 out and put our earliest finishing activity, A1, in its place.
Now, because A1 is guaranteed to finish at or even before B1 finishes, this swap can't possibly cause a problem for the next activity in the schedule. In fact, it frees up the room sooner. So the solution is still optimal, but now it starts with our greedy choice. It's a safe move that always keeps us on the path to an optimal answer.
All right, that's enough theory. Let's get down to brass tacks. What does this look like when you actually sit down to write the code? And more importantly, how fast is it? When we talk about how long this takes, the biggest piece of work is sorting the activities by their finish time. That's a classic O of n log n operation. After the sorting is done, all we have to do is one single fast pass through the sorted list, which is just O of n. So the sorting is the bottleneck, which makes the whole algorithm's time complexity O of n log n. Of course, and this is a great point to make in an interview, if you're told the input is already sorted for you, then the complexity drops to a lightning-fast O of m.
And what about memory usage? Well, that depends a little bit on your implementation. If you're allowed to sort the list you're given directly, what's called an in-place sort, then you only need a tiny, constant amount of extra memory, which we call O1. If you have to make a separate copy of the list to sort it, then that copy will obviously take up ON space. And finally, the list of chosen activities that you return is going to take up space too, proportional to how many you select.
Okay, so you're in the interview. You get this question. How do you knock it out of the park? Here is your step-by-step playbook.
Just follow these 4 steps. 1. Define the problem. Show you understand what's being asked. 2. Solve it. Propose the greedy strategy of sorting by finish time. 3. Justify it. This is the part that makes you stand out. Briefly explain the exchange argument to prove it's correct. And 4. Analyze it. State the time and space complexity. You hit those 4 points, you've given a complete A+ answer.
And be ready for the follow-up questions. A good interviewer will push you. They might ask, what if each activity has a value and you want to maximize the total value, not the count? Well, our greedy approach fails there. You need something like dynamic programming. Or, what if you have to schedule all the activities using the fewest rooms possible? That's a totally different problem. Being aware of these twists shows you have a much deeper understanding.
So at the end of the day, the magic of this solution is that by making the locally optimal choice, by picking the activity that finishes earliest, we always leave the maximum amount of runway open for future choices. It's the safest move every single time, and it leads to the globally best result. Which leaves us with a fun thought. What other big, hairy, complex problems out there are just waiting for us to find that one, simple, safe, greedy move that untangles the whole thing?